Okay, thanks, Joscha. Yeah, I'm going to talk about the macroevolution of parareptiles, so this rather enigmatic clade of early amniotes. I have to say that this project is actually part of a larger project that tries to disentangle the macroevolution of all early tetrapods. And yeah, so the parareptiles are just a part of it, but I haven't finished all the data collecting, so I'm going to focus just on this clade for now. Before I get to the actual topic, I would like to thank my supervisors, Mike Benton, Marcello Ruta, and Alex Dunhill. I would also like to thank the Paleobiology Research Group at the University of Bristol and NERC for funding this PhD. So what are parareptiles? So it's a small extinct clade, contains just 114 species that lived from the latest Carboniferous up to the late Triassic. They were globally widespread, were quite diverse in terms of ecology and morphology, also quite diverse in terms of body size. So you have small critters with a snout vent length of less than 15 centimeters, and also these large, bulky herbivores that are up to 3 meters long. You also see them actually. Pictures here, not the way they should be. Well, despite these properties, in recent macroevolutionary analyses, the parareptiles have been largely neglected, so I think it's also further incentive to have a look at this clade. So what you see here is a phylogeny of parareptiles, so it's part of this informal supertree of all early amniotes that I've assembled in the last couple of months. It has been dated with the equal method as proposed by Busatti et al. In 2008. I've also tried the Carl-Free method. The problem is, well, it actually works for parareptiles, at least you get some valid results, but it doesn't work for other clades. So I still have to figure out why that's the case. If someone has any suggestions what to do, then I'll try that as well. So what I've been doing so far was assembling this informal supertree of all early tetrapods. As I said, I'm just going to focus on the parareptiles for now. At the same time, I've collected data on proxies for body size. I also assembled a simple completeness index, so it gives an indication of the preservation quality of specimens known for the species of early tetrapods, the stratigraphic range, and also information on diet. Yeah, here we have the raw taxic richness, so just the number of species per time bin, and for parareptiles. And as you can see, throughout the Paleozoic, you have several peaks and troughs in the diversity of parareptiles. You have this massive peak in the Wardian. And what's also apparent is that actually the end Permian mass extinction event did not have a negative effect on the overall diversity of parareptiles. Right afterwards, you have a peak in diversity in the Indian. Afterwards, the diversity decreases rather rapidly. This fades then out, and the clade goes extinct at the end of the Triassic. Well, as we all know, the fossil record is not complete, and therefore taxic richness might not be the best estimation of the actual diversity of parareptiles. Different methods have been proposed to overcome this problem. Here I'm using the phylogenetic diversity estimates, and instead of just counting the number of species per time bin, I'm counting the number of lineages per time, so this also accounts for ghost lineages and range extensions. And that's what you get for parareptiles. So the black curve is the median of the phylogenetic diversity estimate for parareptiles, and the gray shaded area gives you the 95% upper and lower quantiles, so it gives you upper and lower boundaries. And what you can see here is that throughout the Paleozoic, actually the increase in the diversity of parareptiles is rather steady, so you don't have the several peaks and troughs as seen before. You no longer have this massive peak in the Wardian. What you still have is that the end Permian mass extinction event still didn't have a major negative impact on the overall diversity of parareptiles. And indeed, right afterwards, we have this massive increase in the diversity of parareptiles. Otherwise, it's actually pretty similar to what we have seen with the taxonomic richness. Yeah, this already brings us to body size. So this is actually one of the major topics of my PhD, trying to disentangle how body size has changed through time within early tetrapods, in this case for parareptiles. So I've chosen femur length as a proxy for body size. There would be better ones like the diameter of femora and the diameter of the humerus as proposed by a computer net around 2012. The problem is just to get those measurements, and furthermore, often these skeletal elements are crushed, so actually they're probably not that reliable to use. So in the end, I use femur length. Still, the problem with parareptiles is that there are only a few taxa, only 30 taxa where femora are known. So I had to cheat a little bit and use skull length to estimate femur length. I initially went with an ordinary least squares approach, then went on with a phylogenetic generalized least squares approach. In the end, I decided to use the OLS just because the PGLS doesn't work for all the timescale trees that I have. Has to do probably with the sample size, so you get a flat likelihood surface if you want to estimate the lambda parameter, so this parameter that indicates you how much phylogenetic signal you have in your data. But anyways, those are technical details, so I went with the OLS approach, which has been done before in the literature. And that already brings me to the models of trait evolution. Again, I'm not going to talk much about it. We already heard a little bit about this in the morning. Essentially, the idea behind those models is to account for the fact that different species are related to each other and have a shared evolutionary history through the phylogeny, and then this translates into the body size data. So here we have the Brownian motion model. And the idea behind this is actually just a stochastic, continuous time random walk where changes from one time to the next are drawn from a distribution with a mean 0 and variance sigma squared. And of course, if you increase the sigma parameter, then you get a higher variance. But the important fact is, of course, that if we look at the expected variance, this increases linearly through time, so it's just time multiplied with sigma squared, so our evolutionary rate. Well, the Onstad-Nürnberg model that we have also seen today is kind of similar. It's just an extension of the Brownian motion model. The thing is here that the trait values are drawn towards an optimum value, and the parameter alpha gives you the strength of attraction to this optimum. Otherwise, it's pretty similar. So again, the expected variance increases linearly through time. Yeah, so this already brings us to some of the results. So here we see the results for the estimated femur length, and as you can see, the Onstad-Nürnberg model is clearly favored for parareptiles. This holds also true if we use other possible proxies for body size, like skull length or mandible length. So it's always the OU model that's favored. The exception is if we just look at femur length alone, so without using those estimated values, then we actually get trend model that's being favored, but this is probably just due to the small sample size. So overall, we could say, well, actually, the OU model is pretty well favored by our data, and we could accept that. There's one problem, however, and I guess this also applies somewhat to talk that we have heard today. So there's this new paper out here by Cooper et al. That has shown that for small paleontological data sets, the Onstad-Nürnberg model is often incorrectly favored over more simple models. And that's something that needs to be taken into account. So the authors of this study proposed to use either Bayesian methods or simulations to overcome this problem. That's something that I haven't done so far, so what I'm showing you here is just some preliminary results. So far it seems that the OU model is the best one, but additional studies, additional analysis are needed to be sure about that. If we just look at the body size distribution within parareptiles, one might argue, well, I would expect to see actually heterogeneous rates across my phylogeny, so changes in the evolutionary rates across different branches. So in blue indicated you have these very large bulky herbivores, the parasaurs, and you could actually expect to see changes in evolutionary rates. So far we have just looked at homogeneous rate models, except for the early burst model and the trend model. So I've tried also to model heterogeneous rates for the parareptiles. I've used stable traits, and it appears that the evolutionary rates on the branch leading to the parasaurs are actually 4 times higher compared to the homogeneous rate model. It's even 10 times higher for the Procolophonidea. Great. Problem is just that actually the heterogeneous rate model, performs worse compared to the homogeneous, compared to the homogeneous rate model. So I've been using here the Brownian motion model with a homogeneous rate and the Brownian motion model with a heterogeneous rate, and it turns out that actually the homogeneous rate model performs better than the heterogeneous one. It's a little bit difficult to explain. It could be, again, too small a sample size, but I think there's a possible other explanation. That's, as we have seen with the homogeneous rate models, it was the OU model that was favored. So actually what I'm going to do now is to use a heterogeneous rate model with an OU model, possibly also fitting different trait optima, and then see whether I still get the same result or not. Yeah, and that already brings me to the conclusions of my talk. So we have seen that the overall diversity of parareptiles was not negatively affected by the end-permeable mass extinction event. We'll then, I think, later on see some other clades, especially synapses, where that's not the case. Preliminary analysis indicate that the OU model is favored, but again, there's more needs to be done to be sure about that. And it also seems that the heterogeneous rate Brownian motion model does not outperform a homogeneous Brownian motion rate model. But this is something where I have to have a closer look at. And that's it. Thank you very much.